Okay, so the next thing that we're going to do is we're going to have a look at the reactions of acyl chlorides, because it's a really common reaction and the mechanism for it is something that's assessed quite a lot as well. Even if it's not drawing the whole mechanism, it's completing part of a mechanism which we know our exam board is moving more towards. So, there is a difference in electronegativity between the carbon and oxygen in an acyl chloride. The oxygen pulls the electrons ever so slightly more in that covalent bond towards itself, which makes it have a partially negative charge, and our carbon a partially positive charge. As a result, a nucleophile, which we know is a lone pair or an electron pair donor, we know a nucleophile would be attracted towards that partially positive carbon. For example, water. The oxygen has two sets of lone pairs on it. Therefore, the lone pairs, which are electrons, are going to be attracted towards the partially positive carbon, opposite charges attract. Remember, our curly arrows show movement of electrons. So electrons are going from the oxygen towards the carbon, not from the carbon towards the oxygen. These electrons that are doing the attacking. As these electrons move towards the carbon, the electrons in the carbon to oxygen bond, they start to repel a little bit. And when they start to repel, they move towards the oxygen that the carbon's bonded to. Both pairs don't move towards the carbon and oxygen. Remember, it's a double bond, so therefore I've got two electron pairs. Only one of them would move towards it. Only one of them moves towards it so that carbon still has its 4 bonds. So at this point, the carbon is still bonded to the chlorine, and it's still bonded to the R group. However, one of the electron pairs in the carbon to oxygen has been repelled towards the oxygen, which now makes that an oxygen with a negative charge, a lone pair sitting on it that's from the bonding pair, and a single bond to the carbon. But what we've also done is we've added this nucleophile, which now puts us in this weird complex that we don't particularly like. The end product from this is a carboxylic acid. So our end product looks a little bit like this. So we need to think, how do I get from here to here? Well, I've got to actually add 3 arrows onto this step. I could do them as separate steps, but I can simplify them down to 1. Well, I need to reform the carbon to oxygen double bond. So I know that needs to get remade. If I remake that only, carbon will have 5 bonds, which it can't have. This mechanism is called nucleophilic addition-elimination. There's a hint in the name. I add a nucleophile, which I've done, nucleophilic addition, but I also have to eliminate something. Well, on this starting species that we have on this reactant, I've actually eliminated a chlorine. There's no chlorine left at the end. So that carbon to chlorine bond breaks in order for the elimination step to take place. So that's great. I can reform the bond and I can remove the Cl. So carbon would now have 1, 2, 3, 4 bonds. But I've still got this situation here. Well, our difference between this and this is that this oxygen has got an extra hydrogen. And it's positively charged. Well, if that bond breaks as well, I can form my carboxylic acid, but I'll also produce something else. I've eliminated an H+, and I've removed a Cl-. I'll also produce HCl. An important thing to note is this is hydrogen chloride. It's not hydrochloric acid because it's not dissolved in water. I've produced hydrogen chloride. I've produced HCl. So this mechanism is worth 4 marks. It's for my initial attack from the nucleophile towards the carbon, from the breaking of the carbon and oxygen bond. My 3rd mark is for the intermediate structure. So that's without intermediate. That's without all of the arrows. And my 4th mark, unfortunately, is for all 3 of those arrows. But this mechanism is the same mechanism that we can apply just by swapping around our nucleophile. So if I change the nucleophile to an alcohol, for example, the reason an alcohol can act as a nucleophile is because it has an OH. So let's say I pick the CH3, I pick methanol, sorry. The lone pair on the oxygen can attack that partially positive carbon, remember difference in electronegativity. That will therefore repel the electrons in the carbon to oxygen bond towards the oxygen, because I'm introducing electron density, so we'll repel other electrons. I'm now left with that central carbon, still bonded to the Cl, still bonded to the R group. It's now got a single bond towards the oxygen because one bonding pair has moved towards it. It's negatively charged, do not forget the negative charge, because it's gained that electron. And I've added in this nucleophile. Same principle, I reform that carbon to oxygen double bond. I eliminate the Cl, and I also lose that additional hydrogen. So now what I've formed is that carbon still bonded to its initial R group, our C double bond O, now bonded to another oxygen, and a CH3. So over here I've formed an ester, because I've got a C double bond O, and inevitably I'll also produce hydrochloric acid. This is different to the previous one because I formed a C double bond OH, which is a carboxylic acid. I'll remove my definition for that. So when I have an acyl chloride plus water, I form a carboxylic acid and HCl. When I have an acyl chloride plus an alcohol, I'll form an ester and HCl. So these are already two different types of reactions that we can see an acyl chloride can undergo. There's another two reactions that an acyl chloride can undergo, whereby it still reacts with a nucleophile, but this time it can react with a nucleophile that's ammonia. And it can react with ammonia because ammonia has a lone pair on the nitrogen. The lone pair is going to attack the partially positive carbon, propel the electrons in the bond towards the oxygen, and now formed this weird nitronium complex. Still the same mechanism in terms of that. And this still happens as well. But I don't produce HCl as the byproduct here, because it's not the chlorine that will that Cl minus, that chloride that will accept that proton. It's actually another one of the ammonias, and you would have seen a similar thing in nucleophilic substitution. You'll have this reaction takes place in excess ammonia. The first one acts as a nucleophile because it donates an electron pair, whereas the second ammonia is accepting an H+. So our second ammonia acts as a base. So let's think about what we form. I've got a C double bond O and my H or my R group, that would have been there. No longer a Cl, but I have got an N and another two hydrogens. Remember that hydrogen's not there anymore because an NH3 has taken it. So I've got a nitrogen with two hydrogens. This is called an amide. The sign of an amide is when there's a C double bond O directly bonded to a nitrogen. This is an amide link. So I formed an amide in this reaction. But my byproduct, as I said, isn't HCl. It's not HCl because it's not the Cl minus that accepts that proton this time. It's an NH3. So if the NH3 accepts the proton...
This is just a reminder to the few existing...
Sorry. So what I'll actually form is an NH4 plus, with that positive charge would then be on that nitrogen, and a Cl minus. So I've got an NH4 Cl minus. You may find it written like this, which is normally how I prefer to write it, but either will suffice. So I've produced an ammonium chloride, so I've produced an ammonium salt in this. So thinking about what I've done, I've reacted to an acyl chloride plus ammonia, where I've had 2 moles of ammonia, and I've produced an amide, and I've produced an ammonium salt. That's what's happened there. There is still another nucleophile that an acyl chloride can react with. I know that we've just done it reacting with water and an alcohol, and we've now just done it reacting with ammonia, but there's still one more. So an acyl chloride can react with an ammonia derivative. Sorry, I know I used an R here and a hydrogen here. It can react with an ammonia derivative, and the ammonia derivative it can react with is an amine. So that's when I have at least one of the hydrogens that would have been ammonia has been substituted with an R group. I normally just write it as NH2R. But for now, we'll just draw it like this so you can have a quick recall of the structure of an amine. This is an example of a primary amine, but that's a whole other thing. So the nitrogen has still got a lone pair in it, therefore can still act as a nucleophile. We'll attack that partially positive carbon, and one of the bonding pairs will move towards the oxygen. Still got my RCO. At this point, we've done this mechanism now 4 times, so we will have seen part of this before. I reform the carbon to oxygen double bond quite quickly, and I eliminate the Cl. I also still lose a hydrogen. Every single mechanism we've done, we've lost that hydrogen. What have now formed? An R, still bonded to the C double bond O. That C double bond O is now bonded to an N H R, because that H isn't there anymore. So it's now bonded to an N, H, and an R. You might be thinking, how is that different? This is what makes it different. It's no longer just an amide. It's still an amide because I've still got a C double bond O and an N, but it's called an N substituted amide. It's called an N substituted amide because the nitrogen in the amide has been substituted with an R group, and we'll look at naming it somewhere else. So thinking about what I'll form, well, I don't produce an ammonium salt this time. Something still does accept that hydrogen. Something still does act as a base to accept the hydrogen, but it's not ammonia, because I don't have ammonia. What I do have, however, is the amine. So it's the amine now that can act as a base and accept that hydrogen. So thinking about what I've then formed, if that NH2R has accepted an H+, I've then got an NH3R, which is now positively charged, and my Cl minus from this chloride ion that I've eliminated. So my final one is an acyl chloride plus an amine will go to an N substituted amide plus I'm going to call it a quaternary ammonium salt of some form, which is not quite, but it's okay. We'll look at that later. But there, that's just your acylation reaction. So the reaction's acylation because it's adding acyl groups, and your mechanism is nucleophilic addition-elimination. You're not expected to learn any mechanisms for any reagents, any conditions, for this, but you should obviously be able to identify your reagents as the different acyl chlorides and nucleophiles.